the afternoon by Daniel Pomerleanu, who will tell us about one connections and one spectra for final management.
Okay, so I'm just continuing my talk, but I want to remind people where things were. So the main thing we're trying to explain is the proof of this theorem here, which says that if you have a smooth Fano manifold which has a smooth anticanonical divisor, then the quantum connection has a singularity of unramified exponential type, and and then there's additional facts that the regularized formal monodromy, which, if you quickly recall what exponential type, what it was about, is decomposition into a regular piece. So whenever we have a regular singularity, there's a well-defined monodromy, and we're saying that the eigenvalues of those are roots of unity, and further, I'll explain this bound on the Jordan blocks when I get there. So just sort of recall the mirror symmetry picture from last time. So there was this kind of Gauss-Monod system, which you can formally construct so you start with a proper Landau-Ginzburg model, and you cook up this Gauss-Monod system, which, after you invert Q, is the mirror to quantum cohomology, but it's a already a well-behaved polynomial D module, and it's and I'll explain in a second why this is when you pass to C star, why this gives you a module of exponential type. So there's an algebraic argument that we'll try to imitate in symplectic geometry. So, but the first step to doing that was to hook up in symplectic terms the mirror to. So I think after you invert Q, this becomes quantum cohomology in mirror symmetry. But what is the actual polynomial D model that you have before inverting Q? And that was this. We got some way to doing it. So you'll recall that there was a sort of purely symplectic. So the differential forms on Y is mirrored to symplectic cohomology, and then there's a distinguished class in symplectic cohomology given by counting symbols that pass through the divisor. In this case, transversely, and are asymptotic to the Hamiltonian orbit in the interior. So this is more generally, which entered into our discussion last time. You could consider things of tangency and more refined constraints, but just the superpotential itself is the count of things that intersect once. And so what we did to construct the Gauss-Monod system is we said, okay, this is like cohomology is an L-infinity algebra. I have this element which, for sort of, because we're in the anti-canonical case, this is a special feature. You have very good control over what the gradings are. So all the gradings are in non-negative degrees. So Q is a variable, a formal variable of degree 2, and this, just for formal reasons, is already in Markov solution. The next, if you had Q squared, you'd need something to make it a total degree 2. You'd need something of negative degree, which the range of the change of concentrated at non-negative degrees. So then you can make some variations. So you can just twist the differential by this Markov element, and you can also invert Q. And the theorem, or the sort of first thing you want to know, is what's the relation between this and quantum cohomology. So it doesn't have the expected properties. So what we prove is that there's a sort of isomorphism between this a vector space like this, where which is Q linear on the factor that's this first component over here. And then and just because of that, after, even for grading reasons in this case, the degrees of those classes are really just homological degrees on D. So just for grading reasons, the Q will move everything into the first component, and after you invert Q, you end up with basically with the state space that is the correct homology. And then so if you're familiar with mirror symmetry and non-commutative geometry, you'll notice that back here, maybe I put the aspect right way. There were two components of the differential. So here we have the de Rham differential and the deformation, and symplectic homology is mirror to differential forms without the de Rham differential. If you want to include the de Rham differential, you need to include also the loop rotation action on symplectic homology. So you do think S1 equivariant. So okay, so that was so there was an S1 equivariant version of the result where you consider, so you'll recall that S1 equivariant symplectic homology became an L infinity module over the symplectic cochains, and you could use that use the Markov tunnel to twist the S1 equivariant symplectic homology, and this also had a so U is just the equivariant parameter that also has degree 2, and again you can identify what this thing is. So this is really the A model of Gauss-Monod system, and then if you invert Q, then again you get quantum homology. The state space is where really the quantum D module lives. So the U here is what Hiroshi was labeling said. Okay, so there is one more piece of structure here that so to complete this mirror correspondence, to set it up, there was one additional piece of structure, which is this D module structure, and that so where does that come in? Well, what you need to construct is a D module structure on this Gauss-Monod system. So, and the way you do this is so you begin by saying, okay, I start with some flat over over Q, and I consider like a naive bit differentiation, just literally differentiating the cochains with respect to Q, and just by the some kind of calculus, what this works out to be will be sort of this operation, naive differentiation, fails to commute with the differential, but but it's clear what you can calculate what the commutation relation is, and it ends up being sort of deformed Lie bracket with the derivative of your Markov-Ton class. In this case, again, the Markov-Ton class is just Q theta, and so it ends up being deformed Lie bracket with the deformed Lie action of theta, and it's just a general fact that in symplectic homology with it's a totally general fact. So this construction works with any Markov-Ton elements. It has nothing to do with the specific geometry of a complement of an anti-canonical divisor. So this operator is not null homotopic. If you multiply it by U, then it becomes null homotopic. And so there's an operator, which kind of obviously on the Markov element, which satisfies this Cartan homotopy equation. And what that tells you to do, what that means is that in particular you add, you take naive differentiation, multiply it by u, and add this Cartan homotopy, then you get that's a chain operator. So it defines kind of a connection in the direction u ddq. But after you invert u, of course, you can throw away you can get an actual honest connection. So the fact that connection only exists after you invert u is kind of a Griffith's transversality property in non-commutative geometry. So what? Let's see. I'm going to try to probably, if I sit here and explain moduli spaces, people will just be confused. So maybe I'm going to elide the construction. I'm happy to explain to anyone who's interested in it. But there's I think in principle, this is like, some of the dysfunctional calculus of BD algebras, but there's a very nice explicit way to construct the Cartan homotopy that we do in the paper. And so the theorem that's actually in our paper is that whenever, so what I call theorem A way back here. So whenever there is an isomorphism between these two groups, the cohomology and the deformed symplectic cochain. So the non-equivariant statement, then this module here that I've constructed, this D module, is of unramified exponential type. So that's the theorem that we proved. And of course, when you take the equivariant version of the identification, which, if you work hard enough, you can show is an identification of modules over the Weil algebra, then you get the full statement. But you get the main theorem that I was stating before. That's the benefit of having a very explicitly defined map, is that it's not, once you have the map defined, it's not hard to prove that it intertwines with connections. Okay, so let's go back a bit, and I want to go back to this to tell you a bit of why the Gauss-Ammann system is a module on unramified exponential type. So let's start with another variable. Make another formal variable, and identify the Weil algebra in this new variable t with the Weil algebra in Q via this Fourier transform. And if you start with a module over WT, then the Fourier loss transform of it is just you take the same vector space, but now view it as a module over WQ. And just by definition, it preserves homonomicity, and it's a nice operation. But in particular, it sort of exchanges two categories. So the natural category is the category of regular modules with regular singularities, and so you start over here with holonomic D modules with regular singularities. Then the Fourier Laplace transform of it becomes actually non-singular on C star. And if you look at the the associated connection on C star, then it has a regular singular point at Q equals 0 and one of unramified exponential type at Q equals infinity. So it's kind of more regular singularities are more. It's easier to sort of understand how you might produce them. So the idea will be to, so if we come back to the Gauss-Ammann system, let's talk about that. So So the basic idea is, okay, over the regular locus, I throw away all the bad points, and I restrict the Gauss-Bonnet system to the regular locus. Then in that case, just over the regular locus, what you have is the Gauss-Bonnet system is a sheet as in the derived category of an isomorphism between this Gauss-Bonnet system and the sort of like Gauss-Bonnet connection that's defined by Katz, sort of the classical thing that you read about in whatever book you like, Wozniak, or Katz-Oda, Gauss-Bonnet connection. So these complex upper shifts, these become isomorphic. And then it's then a classical fact that so when we're looking at the Gauss-Bonnet system, we're looking at the connection in the Q direction, but if you think of that as being actually the base direction and the Q operator as being the differential operator, then Q corresponds to this Gauss-Bonnet, the actual Gauss-Bonnet connection that just moves the cohomology of fibers. And then it's a well-known theorem that this has only regular singularities. So due to many people, the proof that's most relevant to what we want to talk about here is due to Katz. And then these other facts about bounds on the Jordan blocks and having quasi-impotent monodromy, these are also statements that are proved by these people as well. So so this is what we want to, this is what we're trying to imitate. And luckily, so this is sort of saying something about Katz's approach, because it's the one that generalizes nicely to non-commutative geometry. So the idea in Katz is to consider sort of things over a field of characteristic of P bigger than 0. And so let's say you have a smooth scheme over some perfect field of characteristic P bigger than 0, and let's say you have some flat connection over that, then something you can do in characteristic P is you can consider its P curvature. So the P curvature is, it's defined like this. So, in characteristic P, if you take a vector field and you iterate it P times, that itself is a derivation. And then the P curvature is what you get by looking at the connection with the P power, this sort of difference here. And the statement is basically that if you have a ring, so you start with some ring of finite type over Z, and you want to assume that basically the fraction field has characteristic 0, and then you have a curve. What geometrically connected means over basically if you pass to the fraction field part. But so you start with a smooth geometrically connected curve over Q, and you have a flat connection. Then what you want to know, which is, so you want to know that it's nilpotent, that it's nilpotent of some nilpotence index nu. And what that means is that nilpotence means that there's so for any prime, so you have a filtration. Then so B nu will be such that on successive quotients, the P curvature vanishes. So that's like over VI mod VI minus 1, the P curvature vanishes. And if that's the case, then basically if you pull back M to the generic point, then that has regular singularities, and quasi-nilpotent monodromies. And this exponent here means what this exponent is, so the relation between the index of nilpotents and this exponent is the size of the largest Jordan block. So the Jordan blocks all have of the monodromies are all of size of those nu.
What do you mean go back to the generic?
Well, I just mean tendering with the fraction field. Yeah.
So what is this tax and A7 at all?
What?
What is this tax about? From A7 at all?
Where is it from?
Sneak tax actually.
Let's see. So it's in he has a paper called it's in public, it's in the IHS. I don't know the name. I can send you the paper. Maybe it's I don't. It's in a paper. It's an actual paper, but the title is yeah. I'll send it to you. But okay. So what you actually need to do though in characteristic P, so there's another part to the argument, which is of course you need to prove that you actually have that you can produce this filtration in characteristic P. And so the way that, so there's kind of a, what's this filtration? Well, this filtration that exists in characteristic P is called the conjugate filtration. And so, so the way it's defined, it's sort of a nice, you can always learn, try to explain something that's in graduate, or could be in graduate algebraic geometry. So let's say you have the Frobenius. Let W be the Frobenius, and then let's phase change it. So we're going to go what? Larger. Okay. I have a problem. I have a problem with that my whole life. So I'll try to get it right now. So then you have it. This is the starting morphism with respect K, and then this will be the phase change. So this was the Frobenius twist, and then so the absolute Frobenius is going to be so the absolute Frobenius is a map. Sorry, the relative. What I want is the relative Frobenius. So, like this, so that what this does is basically factorize. So there's an absolute Frobenius here, and if you compose this one with this natural map, you get the absolute Frobenius. And then if you stare at this diagram. Then what you get is you get a spectral sequence actually. So you can just because you kind of old school algebraic geometry, you call this F, then you get a spectral sequence with the composition of functors, and it becomes a spectral sequence from this this thing. So the de Rham complex here, and it converges to the de Rham homology of Z over K. And what's interesting is, so this you can identify as further as so there's this Cartier isomorphism. So this one here by the Cartier isomorphism, this whole cohomology becomes identified with in each degree. So omega q over Z prime over K. So this is just maybe the inverse Cartesian isomorphism, but the outcome here is sort of a new, so you have a filtration, well, you get, at least, let's assume that maybe this, I don't know what you need to assume, but in any case, maybe you want to assume the lift, first of all, assume that this Durand spectral sequence degenerates, but this what you get is a novel, a new filtration on the existing characteristic P on the Durand homology of your initial variety Z. And so this is sort of the picture that we're going to try. Well, not me. Somebody already managed to work out in non-commutative geometry. And this is the reason I'm explaining this, even though it's not my work, is because this is obviously like an important part of the argument. So I thought I should at least try to explain, in the spirit of a short course, what's going on here a bit. So let's say you start with some algebra functions on a smooth irreducible curve over C, or any field of characteristic 0, and then you have a DG algebra over A, which is free, and I deleted something. Oh no, I didn't. Okay, I put it here. So then let's suppose that this is smooth and proper DG algebra over R. Then the theorem is that the Getzler connection, the Getzler-Gauss-Manin connection on the periodic cyclic homology has regular singularities and quasi-potent monotones. So that's just the direct analog, I guess, even implies Katz's theorem. And the reason I kind of told this story is because the idea of proving this really just sort of, it goes back to Khaled and well, these authors, what they managed to kind of complete the story, but Khaled, what he was, as far as little I understand, what did you say?
That's something that's smooth over I'm experiencing similarities at all, similarities.
When you say regular singularities, you're including, you're compactifying the curve. So you do it over a compact curve. So every point that you compactify the curve. At infinity, exactly. But what Khaled did, so he introduced like a totally new version of periodic cyclic homology. So just for things in characteristic P. So you have, so again, well, I guess, again, I'm not really, we have an expert here. So, but basically, so it's called the co-periodic cyclic homology. And he defined a conjugate filtration on the co-periodic cyclic homology. So in particular, the Hodge-Durand spectral sequence in this case associated with, well, the filtration associated with this conjugate filtration goes from the Frobenius twist of the Hochschild homology adjoined to a formal variable U inverse to the co-periodic cyclic homology. So this is exactly, if you look at this, it's exactly the non-commutative analog of what you have here when you substitute the Cartier isomorphism. And then and for smooth and proper categories, this co-periodic homology is kind of the key thing. Is actually isomorphic to the periodic cyclic homology. So smooth and proper over K. And then what Vologodsky and Petrov and Vaintrub did is sort of take into account the Gauss-Manin connection and prove the relevant, the fact that indeed the P curvatures vanish on the successive filtrations. So Okay, so we want to apply this, and so we have this. So the category that we're going to look at, as I sort of alluded to, is this Fuqua category. So what we do is you take, what are the objects here? So go back a little bit to Fleur theory. I'll try to avoid too much Fleur homology, but basically you're looking at Lagrangians, which are sort of well behaved near the divisor. So in this sort of tubular neighborhood that I mentioned last time. So you have a divisor D, you have this tubular neighborhood, you have your Lagrangian, and you want to assume that it's sort of conical inside of this tubular neighborhood with respect to the primitive. I guess, in fact, it's quite maybe closely related to what Fuqua talked about yesterday, but in the exact setting, there's like a full theory of these things. And, roughly speaking, just like the symplectic homology, we're looking at red orbits. Here, we're going to be looking at red chords between two different Lagrangian submanifolds. Those would be the kind of generators of the Fleur complex. And the differential accounts strips just like in usual Fleur homology. So many of the theorems that are actually needed to apply this NC monodromy theorem are actually already in place. So but basically by actually the arguments that I explained last time, you can show that the degree 0 symplectic homology is just a polynomial ring in a single element data. Just like if you have a proper, if you have a proper Landau-Ginzburg, the algebra functions on the total space, which is the polynomial ring in the superpotential. And but you can do that directly in symplectic homology. And furthermore, additionally, we know that the Rapp category is proper over this polynomial. And that's again closely related to Fuqua's talk, but I'll explain that in a second. And maybe as a technical remark, really, since this is about DG algebras over K, you might be a little bit concerned about how to put this in the DG setting over the polynomial ring. But because sort of as we discussed before, the symplectic cochains again are in non-negative degrees. So there's no obstruction to lifting it to a cochain level linearity. The E2 connected cover of the symplectic cochains is just the degree 0 part. So any like sort of homological linearity that's uniquely to a TG level thing. So you have this Morita equivalence here, and basically the circle bundle. So yeah, let me explain this properness a little bit. It's kind of there's a very simple geometric reason which has to do with the local circle action. So let's say you can imagine that you have you're just in the circle bundle, and you have your divisor, and let's imagine your divisor for simplicity is just like a curve, an elliptic curve, and you have two. If you think about what happens if you have a Lagrangian, or sorry, the boundary is Legendre, and so if you think about what that projects to in the divisor, that becomes sort of those project to kind of maybe inverse Lagrangian submaps, but and so let's just say they're embedded to make things a little simpler, and over each. So if you think about the intersections when you project. If you lift that, basically, there'll be sort of a short, so up here you'll have, I'm a terrible drawer, or artist, whatever you say, there's like a short, if it projects, if your Legendrians project to an intersection point, there'll be a short red chord that lives over that, a shortest red chord that lives over that intersection point. And then because of the circle action, what you have are going to be, you'll have a bunch of other rev chords that come from taking this short one and then applying, and you go like this, and then you further apply a circle action. You can wind around once, twice, as many times as you like. And so for every short rev chord, for every intersection, you actually get, a non-negative integer's worth of rev chords. And then, what the thing is that what we have to prove is that at least the lowest order in the action filtration, that what happens is if you take the short chord and actually multiply it by this sort of this theta function or symplectic homology class that corresponds to like winding around. The sort of the obvious picture is topological picture is true to the lowest order. So that in other words, this class, if you take and multiply by the short chord, that will be equivalent to going to the short chord and then winding around b further time. So there's sort of a filtration argument that says that you generate all the chords just from those short ones. So this is finally generated, which is what it means to be proper. So that's sort of the heuristic. Okay, so now we're gonna apply maybe I should say what's actually missing. Maybe we'll go, I'm not sure. First of all, one thing that's missing is I said it's proper, but there's a smoothness assumption. So we're gonna have to discuss that. It's not going to, this category is not smooth over the affine line, just like the Landau-Ginzburg model is not smooth over the affine line. There's singularity. So so let's have a look at that. Yeah.
The specific model that you have a theta in it in the Hom space in order, is that a parameter, or is this
No, you could try to do something like that. That's what like I was talking about actually, but no. Like I'm saying, like the lowest order, these theta classes are just the theta class, the lowest order piece of it, or lives on the you have a small cap that's asymptotic with this stratum of rev orbits. And then, there could be higher correction. It's just the actual thing, canonical classes. But the lowest order, you can think that it's just this manifold that lines around B time. Okay, and so, okay, so to talk about this Q thing as well as, what after all, like, what's the relationship between the Gessler connection over theta and the quantum connection. So, obviously you can take your deformation and just move it to the, you can take this Mark-Cartan element because symplectic homology cochains are equivalent as L infinity algebras to this Hawkesbury homology, the RAP category. You take the deformation, this Q theta, and you can associate a Mark-Cartan solution by just pushing it forward, and then you can just deform the Hawkesbury homology and get this in this way. And you can also, another thing you can do is you can look at cyclic homology. And I messed up something. Oh, okay, thank you. And so this, so this carries just so Q is a formal variable of degree 2, but which is maybe not the usual, strictly speaking, the usual setting for the Gessler connection, but the algebra works fine. You still have a connection on this cyclic homology. And what did I do? Oh, okay. And you can deform. So the theorem is that you can deform the open closed maps. This is again true for any Mark-Cartan solution to any Lugo manifold. You can deform the open closed maps in such a way that the deformed cyclic homology is deformed is this Gauss-Manin system. So, right, so as I was saying, the remaining steps to trying to actually apply this NC monodromy theorem are to, first of all, what you want to do is we want that if you remove, so in algebraic geometry, it's a fact that you can just remove finitely many points and you get something which is smooth generically. But in non-commutative geometry, that's a priori not so clear. So we need to be able to find this polynomial that you prove that there's a polynomial so this becomes smooth over R. And then, of course, you'd want to know something about the Fourier transform of that in its relation to the quantum homology, to this Gauss-Bonnet system or quantum B module. So this is the idea, and this actually is so the way to do both of these actually goes back to, it's something I learned from Konstantin and Anatoly Pregel back when I was a student. So there's a quasi-isomorphism between the form Hochschild cohomology and the Hochschild cohomology of the family of categories over this K joints T or theta. And let me what this will imply, the way that it's done, it will imply, maybe the proof of this implies that if you start with something smooth and it's the case that you have a smooth category over the ground, so start over C, smooth over C, and if there is an element such that this Q to the M times P of theta vanishes in this deformed Hochschild cohomology, then it is in fact true that this P inverted A is smooth over this ring here. And the reason this works is something called the Kojelel-Tate-Telemann resolution. Basically, the idea is you start with this works for any DG algebra with a central element. So you build the fiber, the fiber algebra, which is the fiber over zero, and you have two obvious, just like you have two obvious functors between the category modules. So you can either restrict or pull back. And so if you start with a DG module over this B naught, then you get a resolution which is of this form here, which so I should say one important point is what's this B operator. So basically, you take this I upper star. So I lower star, I upper star, then you can sort of identify it with two copies of. There's a non-trivial. You have to just as complex as it becomes isomorphic to this shifted by -1, and there's a non-trivial action of epsilon basically of B naught on this thing that you have to spell out, but just as complex as like this, and the B operator is just to take everything. So you kill this and take and move this over to here. So that's the B operator, and so just so what this tells you is that if you take there's a relationship of the Homs in the Homs on B naught are the homotopy fixed points of the Homs on B, but with this S1 action, with this action of B. This non-script B. So I realize there's too many B's. I'm sorry. And basically, if you apply this general fact so you want to apply this to the case where B is A tensor A off over K, and we're looking at the central element, which would be like theta tensor 1 minus 1 tensor theta. then you apply this, then what you get is this statement that I wrote here. The first statement. And so the statement about smoothness. So in this case, we're assuming that our M. Oh yeah, I should say also M. You want to apply this with M being the diagonal. And you know the smoothness assumption said that M is perfect over A tensor A. And basically, if you know, so that means that so if you push forward from V naught, push forward M, you get something which is perfect. So if you pull it back, you get something perfect. So this I upper star, I lower star is perfect. And basically, so all the finite truncations of it, you know, if you look at just Q up to Q to minus N for any N, that's perfect. That'll be perfect. And Q being nilpotent basically says that you know the identity kind of factors through a finite truncation. So so it's just and actually, you know, you have to be a little bit careful because what I just said is about would be over you know over actually without it doesn't say anything about this inverting process, but it works fine. You can deal with that. And so what, you know, what is this saying? What is this really about? So in our actual application, this deformed Hochschild homology, A is like, you know, some representative of the RAP category.
Is T theta here?
P, what?
Is T the same?
Yeah. I just, yeah. Sorry. So in our actual application, what we had is that this deformed Hochschild homology. So A was like the RAP category was, if you recall, this deformed Hochschild homology. Let's say Hochschild cochains of well, sorry, it would be the quantum homology before you invert Q. So after you invert Q, so this becomes quantum homology. And so, you know, and so the what is this P? It basically is it should just have all the eigenvalues of so theta, you know, from what we discussed last time, theta, or really Q times theta over here, that corresponds to the first Chern class. So it'll be the eigenvalues, so that the critical fibers will be exactly the eigenvalues of quantum multiplication by C1 on quantum homology, which again wouldn't surprise anyone in mirror symmetry, but this is how it looks in a non-commutative framework. So okay, and then again using this Kojal-Tate resolution, it solves like all the homological algebra problems. So also using it, we're able to prove this kind of a Fourier transform relationship between the Gessler connection and the and this nabla Q that I wrote down. So if you take so but the difference is actually that the Hochschild homology, or rather the cyclic homology of AT, if you view it as linear over T, corresponds to the negative powers, because if you look at the Kojal-Tate resolution, it has actually negative powers. So when you take POM into A, those become positive powers of Q, but when you tend there, they become negative powers. And so the picture looks a bit different. You have this negative deformed complex, the Q negative deformed complex, and that becomes basically satisfies the Fourier transform relation with the Gessler connection. And this is just purely something about this is purely a fact about DG algebra with a central element. There's no geometry. It's just an algebra fact. What? Oh, it's the specific. I just copied this from our the specific quasi-subordinate down, but it comes from The quasi-isomorphism comes, it basically comes from this visual state construction. This gives you like a nice representative of the diagram, which when you tensor over Q, it basically looks like that. You take that would be like Hochschild, the U equals 0 version would be literally that, and then you can support with cyclic homology. Okay. So how do you finish the? What did I do? Oh yeah, sorry. So how do you finish the argument then? Basically, so you start with well, sorry. So basically, I borrowed this from like an earlier set of slides. So this was now theorem A, which was conjecture A. The last time I gave this talk, you find your polynomial, and then what happens is that what you know is that after you invert that polynomial and you complete it, then that's acyclic, because you've thrown away all the fibers where this like Hochschild homology is supported, and so you're left with nothing. And then using the theorem, then the piece with the negative Q powers, that's the Gessler connection. The piece with the up to this Fourier transform, and the non-commutative monodromy. So basically, you break up this complex which has a bunch of powers, positive and negative powers. The part with the negative powers, that's going to be the by the Fourier transform theorem, that's going to be the Gessler connection, and that has, by the NC monodromy theorem, that has regular singularities. And then the other piece is the Gauss-Bonnet system, and because of this thing is acyclic, that tells you that the two sides are isomorphic, quasi-isomorphic. Now there is a subtlety here because of the U completion. Actually, it's a subtle point. So we have to actually use symplectic geometry secretly hides here, because you have a bounded model for symplectic cochains. Again, like they live in bounded degrees. So the U completion actually doesn't do anything. So hiding this result, again, we use symplectic geometry to show that like when you U complete the positive power, that actually doesn't do anything. So that's a little like technical. I mean, it's a very important point, but maybe not obvious from just the way I said it. And then in the diagram form, this is what you can find this diagram in our paper, and it relates all the different things we've talked about. Now, what about the Jordan blocks? So this thing that I promised to say something about. So what you get is the result is that if you look at the regularized formal monodromies, meaning you take exponential type, you look at the regular piece of the singularity, then I'm doing something. Okay. Then at eigenvalue not equal to 1, the size is bounded by the dimension. And then at eigenvalue 1, actually the size is bounded by the dimension plus 1. And the reason there's a difference is because of the Fourier. So if you're just looking at the Gessler connection in the T or theta space, then all the Jordan blocks are bounded by the dimension. But when you translate that to the under Fourier Laplace transform, somehow the eigenvalue 1 piece is causing some trouble and push the bound up by 1. Just something about Fourier Laplace transforms. And just to say where this bound comes from. So in Petrov, Ventra, Bologodsky, the bound on the exponent is of the size of the Jordan blocks is d plus 1, where d is the highest degree, non-vanishing degree of Hochschild homology. And in the geometric context, again, this comes from the fact that I've said many times already that the symplectic homology has a specific degree bound coming from the boundary of the circle bundle. Basically, the cohomological dimensions of the circle bundle. So you use that, you apply a spectral sequence argument, you get this stuff. So yeah, so I want to sort of maybe say what, there's an obvious kind of question here, which is, so you have these fibers, and it's not hard to show these fiber categories, smooth ones, and it's not hard to show using some homological algebra that what you've got is a smooth and proper like the fibers are smooth and proper categories over C now. It's Calabi-Yau. Okay, and the Calabi-Yau in the proper Calabi-Yau categories. And and their dimension will be their Calabi-Yau dimension will be one less than the dimension of the space. And so it's natural to ask: is there a relationship between that and the Fuqua category of the divisor itself? And indeed, so this is actually kind of looked at in a different way by Seidel. And the conjecture is that, at least in Seidel's work, the conjecture basically, let's make a simplifying assumption that the dimension of H2 is 1, otherwise there's corrections of the statement that are needed. And let's say, just put it again in Seidel's framework, that there's another anti-canonical divisor, so you basically get a pencil of anti-canonical divisors. So you get a kind of a Levsch's pencil, or a pencil. Then after a change of variables, then you get an equivalence of basically the fiber at infinity. So you take the formal neighborhood of infinity, and that should be after a change of variables equivalent to the, I guess, again, the framework, the relative Fuqua category of D with respect to this additional divisor. And then I'll add, just because it's something that I've been interested in lately, you also conjecture, so this is kind of an intrinsically defined mirror map to any kind of quantum manifold, or at least under these assumptions, I'll add that it should be like at least maybe integral or and this Q here, yeah, this, by the way, this Q bar is the Novikov parameter in the I'm out of time. I was going to say something about Steenbrink spectra, but I can just talk to people who are interested in that. Basically, the 1 minute story is that if you anytime you have sort of what Maxime talked about, anytime you have a connection with regular singularities, you have a kind of a Steenbrink, some rational numbers you can associate to this, and then it's sort of interesting to try to think about their properties, in particular semi-continuities, with respect to sort of adding parameters into the Fuqua category. Yeah, I'll stop there. Thanks.